Okay, gentlemen, so today I'm going to be going over the worksheet, the two worksheets from this week, Boyles and Charles law and the Gay-Lussac and combined gas law worksheets. So I'm just going to work through them, show you how to rearrange the equations, and go through everything. So number one on the Boyles and Charles law worksheet was just to convert from degrees Celsius into kelvins. And just remember, Kelvin is degrees Celsius plus 273. So you'll see the values there. And I will put this document up as a key along with this video. So, question number two, a weather balloon has a volume of 30 liters at ground level. What is its volume at 0.6 atmospheres, assuming the temperature remains constant? So, first of all, I like to label my variables. I have a volume, we can call it volume 1, at ground level, which is this pressure 1. So that volume and pressure go together. What is its volume? So V2 is what we're looking for at 0.6 atmospheres. So we're going to set up the equation. This is going to be V1 P1 equals V2 P2. The law is Boyle's law. And then we have to rearrange it. We are looking for V2. No, I have V2 twice there. So we're looking for V2. Let me just put P2 in. So looking for V2, which means we divide both sides by P2 to isolate it. So rearranging, V2 equals V1 P1 over P2. And then you would plug in the numbers, and I'm going to do that and come back. Okay, so you can see that I have filled out the equation. V2 equals 30 liters times 1 atmosphere divided by 0.6 atmospheres, and you should get a value of 50 liters for the second volume. One thing to check, if you want to make sure you arrange your equation correctly, check that the units cancel out. Atmospheres and atmospheres cancels out, leaves you with liters, which is the units you want. So it's a good sign you probably rearranged everything correctly. Okay, moving on to number 2. Again, I'm going to mark my variables as I go through. 2 suction cups are placed together so that there's 7 milliliters, that's a volume, of air between them at 760 millimeters mercury. That's a pressure. So this volume, V1, goes with this pressure. When stretched, the volume inside the suction cups, so V2, becomes 25 milliliters. What is the pressure? P2 is what we're questioning. Again, we're dealing with volume and pressure, so it's going to be Boyle's law. V1 P1 equals V2 P2. And this time, we're looking for pressure too. So we're going to rearrange it and plug in all the numbers. And I will do that and come back. Okay, so you can see I filled out the equation. I rearranged it by dividing both sides by volume 2, P2 equals V1, P1 divided by V2. We have all those numbers. We plug them in. And again, you'll notice I check my units in the milliliters, cancels out. And I end up with millimeters of mercury as my unit, which I want. So 7 milliliters times 760 millimeters of mercury divided by 25 milliliters. And your new pressure is 213 millimeters of mercury, which makes sense. If you expand the amount of space, if the volume gets bigger, you'd expect pressure to go down because the particles are going to hit the sides less often because there's more space between the sides. So, looking at number 4, you have a balloon that is 5 liters. That's a volume, call that volume 1, on a 33 degrees Celsius day. That's a temperature, T1. But before I do anything else with it, I'm going to add 273 to it. So 33 plus 273 is 306. So 306 kelvins. Before I even do any math, I changed to kelvins. You leave it overnight. The temperature in the morning is 15 degrees Celsius. That's T2. And again, you add 273 to 15, and you get 288 kelvins. what will the volume be in the morning? So we are looking for V2. So now we're dealing with volume and temperature, not volume and pressure. So this is going to be a Charles' law equation. Sorry, blank there for a second. Charles' law. So that starts out volume 1 over temperature 1 equals volume 2 over temperature 2. By the way, this means that as one goes up, the other goes up. If volume goes up, temperature goes up, and if volume goes down, temperature goes down. As opposed to a Boyle's law, which is an inverse relationship. As volume goes up, pressure goes down, and as pressure goes up, volume goes down. So when they're multiplied, that indicates that they have an inverse relationship, and when they're divided, that indicates that they have a direct relationship. So back to the problem, we are looking for the second volume here. So we're going to rearrange this by multiplying both sides by T2, and then we'll plug in all our numbers. So I've rearranged the equation. Volume 2 equals V1 T2 divided by T1, and then I plugged in all the appropriate numbers. So 5 liters times 288 kelvins divided by 306 kelvins. Again, you can check to see that your units cancel out. Kelvins on the top and bottom cancels out. I'm left with liters, and I get V2 being 4.7 liters. And that makes sense because as temperature goes down, we would expect volume to go down. Those gas particles are going to push less hard on the inside of the balloon because they're going slower. If they're going slower, they're not going to hit as hard on the side of the balloon, so the volume will go down. So as temperature goes down, volume goes down. There's a direct relationship there, and we see that here. So our answer makes sense. Okay, so I've done number 2. It's pretty straightforward, similar to number 1. So I'm not going to go over that in detail. The answer will be available for you. Just make sure you convert Celsius to Kelvin, otherwise you'll get the wrong answer. So I'm going to look at number 3. Number 3 says the volume of cake batter increases because carbon dioxide expands with temperature. The gas in the batter goes from having a volume, this will be the first volume, of 0.5 liters at room temperature. That gives us the first temperature, 25 degrees Celsius. Make sure to convert to kelvins. To a volume of 0.8, that's the second volume, in the oven. What is the temperature in the oven? And name the law. So we're dealing with volume and temperature. Again, that's going to be a Charles' law equation. Volume 1 over temperature 1 equals volume 2 over temperature 2. And as I mentioned in the previous video, whenever you're looking for something in the denominator, if you have one of these equations, I find it easiest to just flip the equations, invert both sides of the equation. So it's an equation, you can do the same thing to each side. So instead of just trying to rearrange it by cross multiplying, which again you can do but tends to lead to mistakes I've found, I'm going to take one extra step and just go, okay, T1 V1 equals T2 V2. So these two fractions equal, then their inverses must also equal, so the equation holds. And then if I'm looking for T2, it's much easier to see. I just multiply both sides by V2. So the final rearrangement will be T2 equals T1 V2 over V1. So we have all those numbers, and I will plug them in, and we'll see the. Okay, so when I plug in all the numbers to the rearranged equation, we get a second temperature of 477 kelvins. Be careful. Sometimes it's weird. A lot of people accidentally put Celsius there, but watch your units. We put in kelvins here. The liters cancel out, so your temperature you get out should be in kelvins. And it's perfectly acceptable to give the answer in kelvins as long as you label it correctly. If you want to go convert that back to Celsius, you can do that. But I'm perfectly happy accepting it in kelvins. Okay. So moving on to the second worksheet, the Gay-Lussac and combined gas law worksheet. I'm going to do a couple of these problems, and then I will just have the answers for the other ones written up. But I'll do the first one. As before, again, I like to label my variables as I go through. Determine the pressure change when a constant volume gas. So if the volume is constant, we're not worrying about that. At 1 atmosphere, that's a pressure, is heated from 20 degrees, that's the initial temperature, so that'll be T1, to 30 degrees, T2. But these are both Celsius, so immediately 273 plus 20 is 293, and plus 30 would be 303. So make sure to convert to Kelvin. Here we're dealing with pressure and temperature, and of course, determine the pressure change. So we're looking for P2, that'll be our question mark. So here we go. We're going to be using Gay-Lussac's equation, which is P1 over T1 equals P2 over T2. Temperature always goes on the bottom for both Gay-Lussac's and Charles' law. Temperature goes on the bottom, and for the combined gas law, which we'll see. So we're looking for the second pressure. So we'll rearrange by multiplying both sides by the second temperature. So P1 times T2 divided by T1 equals P2. And we will just plug in all the numbers in. So P2 equals the first pressure, which is 1.00 atm, times the second temperature, which is 303 Kelvin, divided by the first temperature, which is 293 Kelvin. Okay, so when I plug in all the numbers, 1 atmosphere times 303 kelvins divided by 293 kelvins gives us 1.03 atms. So not a very big pressure change there, which makes sense if you think about the ratio 303 to 293. In terms of kelvins, it didn't change a lot, so you wouldn't expect the pressure to change much either. However, if the pressure increases, we would expect the temperature to increase and vice versa. So you heat something, you expect the pressure to increase for a constant volume. And our pressure did, in fact, increase. So it makes sense. Okay, so I've worked through the rest of these and given you the work and the answers. They're all pretty similar. A couple things to make sure of. Just check whether the temperature is in Celsius or kelvins. So in some of these problems, one of the temperature, in problem 3, the first temperature was in Kelvin and the second temperature is in Celsius. So just make sure to convert to Kelvin whenever you see Celsius. Other than that, I think these are fairly straightforward. They're all looking for the second pressure, so the rearrangement is the same. Just plug in the numbers and be careful, because you can have more than one unit of pressure. Just whichever one they use, that is what you would get out if you're looking for the second pressure. So that's the Gay-Lussac's law worksheet. Okay, moving on to the combined gas law worksheet. These problems are a little bit more complicated, but you still end up with all the variables except one. You're just rearranging the equation and solving for the one variable. Again, be careful the temperatures in Kelvin, and just be careful when you label all your variables because there are more. So I'll do number 1. If I initially have a gas at a pressure, let's call that P1, of 12 atmospheres, a volume, V1, of 23 liters, and a temperature, T1, of 200 kelvins, and that's already in Kelvin, so we don't have to do anything with that. And then I raise the pressure, so we'll call that P2, to 14 atmospheres, and increase the temperature, T2, to 300 kelvins. Again, it's in Kelvin, so we're good. What would be the new volume? So we're looking for V2. So everything changes. There's nothing staying constant here. Everything is changing. Volume, temperature, and pressure are all changing. So this is a combined gas law problem. And the combined gas law is literally just taking the 3 other gas laws and combining them. V1 P1 over T1 equals V2 P2 over T2. The 1 there. And you can actually see where each gas law exists. If I were to take away the T's on the bottom, and I'll put them back in a second, you get Boyle's law. If I were to take away the P's, you get Charles' law. And if I were to take away the V's, in other words, hold them constant, you get Gay-Lussac's law. So the combined gas law is literally just the combination of the 3 other gas laws. So now we want to rearrange this for the second volume. We're interested in the second volume. And in this case, I actually do think it's pretty easy to cross multiply because you've got two fractions, and it just seems like it's pretty easy to know that you're going to have to multiply both sides by T2 and divide both sides by P2. So if you wanted to, you could do something like this and just draw an arrow, and T2 is going to go up here, and P2 is going to go down here. If that helps you, I'm going to get rid of those, just so the work is clean. And you'll see that looking for V2, you get V2 equals V1 P1 times T2, so multiply both sides by T2, divided by T1 and P2. And we have all these numbers. They're all given to us in the problem. We just have to plug them in and do the math. So I've plugged in all the numbers. Again, if you check the rearrangement of the equation and plug in all the numbers with the units should cancel out except what you want to keep. So we want to end up with a volume, so we want liters. We see kelvins cancels out here and here, and atmospheres cancels out here and here. We're left with liters, and our new volume is 29.6 liters. Okay, for the second problem, a gas that has a volume of 28 liters, a temperature of 45 degrees Celsius, and an unknown pressure, has its volume increased to 34 liters, its temperature decreased to 35 degrees Celsius, and if I measure the pressure after the change, it is 2 atmospheres. What was the original pressure? So I labeled my variables 28 liters as V1. The original temperature, T1, is 45 degrees Celsius, and I immediately changed that to 318 kelvins. And I'm looking for the first pressure. So P1 is my unknown. V2 is 34 liters. T2 is 308 kelvins. Again, change that right away before you do anything else. And the second pressure is 2 atmospheres. So in this case, I'm looking for P1. Yeah, it's a little weird that I'm looking for something that I labeled with a 1 subscript, but it really doesn't matter mathematically. It's inconsequential. So we're dealing with everything changing, so we combine gas law. V1 P1 over T1 equals V2 P2 over T2, and we are looking for, we're looking for P1. So to rearrange, all we're going to do is take, and again, you can do the kind of cross multiplying thing here, V1 down to here, and T1 up to here. So in other words, divide both sides by V1 and multiply both sides by T1. So I'll do the rearrangement and plug the numbers in and come back. So I rearranged the equation, plugged in all the numbers as were given. Your units will cancel out so that you end up with a unit of pressure. So liters cancels out here and here. Kelvins cancels out here and here. And you end up with atmospheres, which is what you want. If you plug in all the numbers through calculator, you will see you get 2.5 atmospheres. So that's the last example I'm going to go through. I will do the last 3 of these and put them up online for keep. And I will come back after that and give you the final. Okay, so gentlemen, I have finished filling out the key here. I will make this available as a PDF or some form online, so you don't have to freeze the video. Couple things: you have a quiz on Friday. It will be 10 points. It'll be basically 4 or 5 of these problems, just like on your 2 worksheets. So know the gas laws, know their names, their formulas, the 4 gas laws we've learned, the names and formulas, and know how to use them. And be careful with your temperatures. Temperatures need to be in kelvins. The lab is due Friday at 6:30. The quiz I will put out. I will publish it on the website and the Google Class site at 10 a.m. on Friday, and you need to get it back by 8 p.m. In the Google form. So be sure to do it that day. You can use any resources except one another, but please do get it done so you get credit. Also, the Gay-Lussac and combined gas law is due Thursday, which will be the day you're watching this ideally, at 6:30. So make sure to get that in too. And again, turn things in on the Google form. That is the easiest way for me to get them, and it will make my life easier and me a little happier while I'm grading your stuff. If you have any questions, come to the Zoom meetings and ask. I can work some problems out at the Zoom meeting or email me, whatever works for you. Okay, have a good day, gentlemen.